This training is part 2 of centrifugal pump construction. It will cover flanges, drive-in pump configurations, priming systems, and materials of construction. Pioneer Pump has standardized on Class 150 flanges per ASME B16.42 on all ductile iron and steel pumps. At normal temperatures, they have a rating of 260 psi or around 600 feet of head. Remember, Class 150 is not the same thing as 150-pound flanges. The high-pressure flange option is Class 300 flanges. These are rated for 680 psi. In a single pump operation, only the discharge flange would need to be Class 300. If the pumps are in series, it is more than likely that the suction will also need to be Class 300 as well. The chart shown lists the specifications of Class 150 and Class 300 depending on pipe size. Notice the increased number of bolts needed for Class 300, and also be aware that the flange thickness will also increase. Pioneer offers 3 main driver attachment options. Option 1 is the horizontal bear shaft, which includes a bearing cap. This configuration is for electric base coupling and guard units, as well as diesel-driven units that utilize a stub shaft. The next configuration is SAE mounted. This is mainly used for diesel-driven packages, and they come in sizes 0 through 5. The third configuration is close coupled. This design has the motor shaft directly attached to the impeller. The motor and shaft are specifically made for this configuration. Priming is very critical to any suction lift application. Priming a pump is the introduction of fluid into the pump to prepare it for working. Priming systems can also enable the pump to automatically reprime itself during operation if loss of prime occurs. Pioneer has 3 distinct priming systems, each with their own strengths and weaknesses. They include Pioneer Prime, Venturi Prime, and Self Prime. The most popular option is our Pioneer Prime. It utilizes a diaphragm vacuum pump to evacuate air from the casing and suction line. The vacuum pump is belt driven from the pump shaft, so it is always running. Our compact priming chamber is the device that allows for fully automatic priming. Depending on water level in the casing, a float ball connected to a linkage assembly opens and closes a valve leading to the vacuum pump. To seal off and evacuate air from the casing, a discharge check valve is also required. Advantages to this design are that it is fully automatic priming and it evacuates the air at 50 cubic feet per minute, allowing for fast reprimes. Another option is Venturi Prime. This design utilizes the Venturi effect, which will be covered in the next slide, to evacuate air from the pump. It requires an air compressor either on the engine itself or mounted to the bearing frame and powered by the shaft. It is not as effective as the Pioneer Prime, but it is cheaper and quieter. It works by having compressed air being forced into a device called an eductor, which creates a vacuum. This vacuum evacuates air from the pump and discharges it through an open hose to atmosphere. Both designs use the same priming chamber. The Venturi effect is defined as a reduction in fluid pressure that results when a fluid flows through a constricted section of pipe. The increase in velocity is balanced by a drop in pressure, which creates a vacuum. This phenomenon works on the basis of the Bernoulli principle. The image shows what the internals of an eductor look like and the flow of fluid. The drop in pressure in the eductor creates a vacuum and evacuates the air from the suction piping. Both lines are then discharged into atmosphere. Our final priming system is our self-prime, also known as wet prime. This design is exclusively used in our trash pumps and requires the casing to be initially filled with water. Once filled and turned on, the air-water mixture is discharged into the water reservoir. The lighter air rises and the heavier water sinks and recirculates. Once all the air is evacuated by the one-way valve, atmospheric pressure forces water up into the suction of the pump. The water reservoir stays full after shutdown, barring no leaks, and can then self-prime upon startup. The chart shown lists the top 5 materials of construction for our pump ends. The numbers 2, 5, 6, 71, and 75 are usually prefixed with an L, for example, PP66S12 L71. The L represents the type of mechanical seal, but the 71 means it follows the materials listed out in the table. As you may notice, the wetted parts are different for each code, but the SAE, shaft, bearing housing, and bracket are all the same. This is because those parts never touch the pumped fluid and can usually stay the standard material. This chart breaks down Pioneer's top 6 materials and lists their respective Brinell hardness numbers, yield strength, magnetic permeability, and some applications and benefits. As a very general rule, applications with pumpages in the pH range of 4 to 9 can often be addressed with standard ductile iron construction as long as the solids content is under around 5% by weight and the solids are not hard. Pumping slurries with solids concentrations above 20% and the resulting specific gravity is in excess of 1 can be done, but these will usually require high chrome iron construction. Pumping brine or any solution that is closer to the ends of the pH scale will require stainless steel like 316 or duplex stainless steels like CD4 MCU. Knowing the pH of the fluid being pumped is critical in deciding what materials of construction to use, but more information is usually needed. Temperature, concentration, and the specific makeup of the solution is needed to make an accurate and effective selection. Chemical compatibility charts are also important to have as a reference when selecting a pump for a special application. The chart shown is a simple reference guide to what materials are required when dealing with the upper and lower portions of the pH ladder. The highly acidic or basic solutions require more corrosion-resistant alloy steels, while the middle of the chart is handled with just standard ductile iron and steel. This concludes part 2 of centrifugal pump construction. We covered the difference between Class 150 and Class 300 flanges and when they are used. We discussed the 3 types of drive-in configurations, which were bare shaft, SAE, and close coupled. The 3 priming systems were explained in detail and the strengths and weaknesses of each. Finally, we covered materials of construction and how you choose the correct material for an application. Be sure to come back for Mid-Level System Design Part 1, where we will cover NPSH, total dynamic head, friction losses, and we will also walk through an example problem calculating total dynamic head of a system.